Good afternoon to everyone. So in my presentation, I'll be giving you overall view on the analysis of DEXLab. The contents of my presentation are as follows. I'll begin with a brief introduction to classification of bridges, the structural classification or the structural configuration of simple DEXLab bridges, an overview of IRC loadings, and then I'll discuss on the analysis of DEXLab by the effective width method and the Piggers method. So as we have also seen from the earlier presentation that IRC has defined a bridge as a structure which has a total length of greater than 6 meters and which is designed for moving loads. A smaller version of the bridge is called as a culvert. Typically, a culvert is a structure which has a total length of not more than 6 meters. So when we look at a bridge structure and as a culvert structure, these are the things what we see. First and foremost, in case of culvert, a culvert has a very simple structural configuration. It simply consists of a deck slab which is resting on two abutments, or in case of a multiple span culvert, there may be an intermediate pier. And basically, in case of a culvert, the slabs simply rest on two opposite edges of the slabs. But in case of a bridge, depending upon the type of the bridge superstructure can have different structural configurations. The most common type of bridges what we see around are the T-beam deck slab bridges. Here, the structural components consist of basically of the deck slab, the girders and the cross girders, again which are resting on piers and abutments. Here, the deck slab rests on the network of girders and cross girders. Further highlighting the structural configuration of simple bridges and complex bridge structures, these are the things what we notice. In case of slab culvert, which is considered to be the simplest form of a bridge structures, we see here that a slab culvert simply consists of a slab which is freely resting on two opposite sides called as the abutments. The configuration may change. We may have an intermediate pier also. But looking at the simplest arrangement, we have a deck slab which is resting on two opposite sides, due to which what we get is a slab that spans only in one direction. So therefore, these slabs are analyzed as slabs spanning in one direction, or simply we say it as one-way slabs. On the other hand, when we look at these typical T-beam deck slab bridges, where the deck slab is resting on a network of girders and cross girders, we see here that the deck slab is resting on all the fours, on all its four sides on the girders and cross girders. Because of this structural configuration, the load that is coming on the deck slab is transferred on all the four sides. Hence, the structural configuration what we get is a two-way slab. Basically, in this case, the slab spans in both the directions. So when I take a cross-section of this simple slab culvert, and if I take a cross-section of this simple T-beam deck slab bridge, so these are the structural components of what we see. So basically, in case of this simple slab culvert, we have just one structural element, that is the deck slab. And this slab is resting on two opposite sides on the abutments. At the ends, we have either a footpath or a curb. And that is all we have in case of a slab culvert. But when we look at these more complex structures, as in case of a T-beam deck slab bridge, we have several structural components here. The first thing what we notice is the deck slab, and then below this deck slab, it is supported by the girders or the longitudinal girders and the cross girders. So the fundamental difference between a slab culvert, the deck slab of a slab culvert and a T-beam deck slab bridge is here. We can see here. In case of the deck slab of a T-beam deck slab bridge, the slab here is resting on a network of girders. Here the slab is supported on all the four sides, forming a two-way action. The slab may be extended beyond the edges, forming the cantilever slab. So when we have to analyze the deck slab, the first thing that we need to understand is what is the structural configuration of the deck slab. So speaking from the structural configuration, we can classify them as slabs spanning in one direction and slabs spanning in the two directions. The simplest case is the one-way slab. Here, the deck slab simply rests on two opposite sides, and when the load is applied on the deck slab, the load transfers to the supports only in one direction. Because of this structural action, we have deformation only in one direction. Hence, we call this as a one-way slab. When we look at a slab which is spanning in two directions, then here what we see here is that the slab is resting on all the four sides on a network of beams. The load that is applied on the deck slab is transferred in the two perpendicular directions. Because of this action, the slab deforms in both the directions and we have a two-way action. Hence, these slabs are designed as two-way slabs. This particular slide gives us an overall picture or the overall procedure that is adopted in the analysis and the design of the deck slab. I'll just explain these steps one by one, and the details of each will be explained in the coming slides. When we have to analyze and design a deck slab, the first thing what we need to understand is what is the structural configuration of the deck slab. So either depending upon the type of the bridge, the deck slab may be classified as having a one-way slab or it may be a two-way slab. The next thing what we need to understand is what are the loads that the deck slab is subjected to. The first and the foremost load or the primary loads are the dead loads, which is derived from the self-weight of the deck slab. And next comes the very important load is the live loads. Now the live loads on the bridge structures are prescribed by IRC 6. So depending upon the nature of the bridge or the design loads that the bridge is expected to carry, the IRC 6 has classified 5 different cases of live loadings. So we'll be seeing these loadings in a bit. So once the dead loads and the live loads have been identified, then we go for the analysis. So depending upon whether it's a one-way slab or it's a two-way slab, accordingly, the slab is analyzed and the design bending moments and shear forces are calculated, and then the designs are performed. So once we have already seen what we mean by structural configuration, that is a deck slab may behave as a one-way slab or it may behave as a two-way slab. The dead loads are derived from the self-weight of the deck slab, which are obtained by multiplying the thickness of the slab with the density of the concrete. The next thing what we need to understand is what are the live loads, or what we mean by these IRC class loadings. So this was already covered in our first day of the presentation, but just to reconnect to those things, I'll just very quickly explain what are these IRC loadings and then move on with the presentation. So IRC 6 has prescribed the live load in the form of two different type of vehicles. So the diagrams which are given in IRC 6 are quite plain. Sometimes for the beginners, it becomes very difficult to really understand what these diagrams are. So I've taken the liberty to take some images from the internet and just to try to show what exactly these loadings looks like. IRC 6 has given the loadings in the form of tracked vehicle loading and wheeled vehicle loading. So here, tracked vehicle loading means it simulates a battle tank. And a wheeled vehicle loading, it means it's a long trailer having multiple axles subjected to various axle loads. So by changing the configuration of these vehicles, the different loading classes have been defined. So very quickly, we will go through those different types of loadings. So IRC 6 has given us these 5 class of loadings: IRC class 70R, IRC class AA, class A, class B, and the recently introduced IRC class, special class vehicle loading. So the loading depends on the type of the bridge. The load, the design load that the bridge has to resist. Based on that, one of these loading combination is selected. So let's quickly see what are these loadings. So the first loading is the IRC class 70R loadings. This loading is prescribed in the form of tracked vehicle loading and wheeled vehicle loading. So IRC class 70R track vehicle loading consists of a battle tank, something like this. The diagram what you see in a monochrome or black and white, this is the diagram that is given in IRC 6. Sometimes it becomes very difficult to really visualize how this is, what exactly this load is. So as I mentioned, I've taken the liberty to add some colorful images here just to make it more interactive. So IRC 70R track vehicle consists of a battle tank. So this weight of this battle tank is 70 tons or 700 kilonewtons. And this length, what you see here, this is 4.570. That is the contact length of the wheel or the track on the deck slab. Then this is the dimension along the length of the bridge. So if I take a cross section and if I look at this vehicle across the span, this is how it looks. So this is one track of the vehicle. This is 0.84 meters. The second is again 0.84 meters. This is the clearance. That's the minimum distance that the vehicle has to be placed from the edge of the footpath or the curb. And we can see here that the load of 70 tons is equally distributed between the two wheels. So this is the configuration for IRC class 70R loading. So if 70R wheel loading is to be adopted, then the wheel loading is something like this as given here. It consists of a series of axle loads. So what are these axle loads? This axle loads could be something like a vehicle, something like this. So we can see here these are these wheels on the either side of the axle, and these axles are transmitting various axle loads. So the first wheel, the first axle in the front transmits a load of 8 tons, and the subsequent axle transfers loads of 12 tons, 12 tons, 17, 17, 17, and 17 tons respectively. So IRC 70R wheel loading consists of a wheeled vehicle whose total weight works out to be 100 tons. Next is the IRC class AA loading. Again, here the loading is prescribed in the form of tracked vehicle and in the wheeled vehicle. So the tracked vehicle again consists of a battle tank. So the fundamental difference between IRC class 70R and IRC class AA loading is the contact length of the wheel that comes in contact with the deck slab. So in case of 70R, the contact length of the track or the wheel was 4.57 meters, whereas the contact length of the track in case of AA loading is 3.6 meters. The other difference what we see is the width of the track. In the earlier case, the width of the track was 840 mm and sorry for the disturbance. In case of IRC class AA loading, so we have the track width of 850 mm and 850 mm. In the earlier case, it was 840 mm respectively. Sorry. So this is the fundamental difference. This was the thing I wanted to highlight here. So this is the contact length of the wheel on the deck slab. This is 4.57 for IRC class 70R, and here it is 3.6 meters. Other than that, the rest of the things remain the same. Here too, the weight of the vehicle is 70 tons. In case of AA loading wheeled vehicle, the code has specified an axle load of 20 tons. Either the deck slab may be assumed for a single axle load of 20 tons or two axle load of 20 ton each. So either of these combination can be used for the analysis of your deck slab. The next and a very important class loading is the IRC class A loading. This is the loading that is used for bridges, for all permanent bridges. So basically this consists of a powertrain and trailing units. The total weight of this vehicle weighs 55.4 tons. So we can see here that the axle loads varies from 2.7 tons to the maximum of 11.4 tons. So this is how the vehicle looks in the elevation, and this is a diagram what is required to be understood, to be read when we are analyzing the deck slab. So this is the plan of the vehicle, that is how it looks from the top. So the center to center distance between the wheel load is 1.8 meters. The next loading is IRC class loading. This is typically used for temporary bridges or timber structures. Here, this loading is very similar to IRC class A loading, except the intensity of the axle loads. So if you can just see here, the axle loads are 2.7, 11.4 and 6.8. The distances are the same, but here the intensities of the axle loads have been reduced from 1.6, 6.8 and 4.1 respectively. The last class of loading is the special vehicle loading. So this loading has been introduced very recently in the latest revision of IRC 6. So here we see we have a prime mover and we have a trailer unit. So this trailer unit consists of 20 axles transmitting a load of 18 ton each. So nowadays we see that we see a heavy movement of very large and very heavy equipment on the roads. So to cater to the demand of such movement of such vehicles, this new class of vehicle loading has been introduced by IRC. Now the total weight of this vehicle is 385 tons. So these are the 5 different classes of loadings which are prescribed by IRC 6. So next thing what we really need to understand is when we design a bridge, when we go for the analysis of the bridge and we have 5 different types of loadings, then the question that comes to the mind is which class of loading is to be adopted for which type of bridges. So the IRC 6 has given very clear guidelines on the type of loading that needs to be adopted. IRC class 70R loading can be adopted on bridges, permanent bridges and culverts, or bridges located on any bridges which are permanent in nature and culverts. IRC class AA loading is to be adopted or can be adopted on bridges located in municipal limits, industrial areas and highways. IRC class A loading, now this is a very important loading where all the bridges are analyzed and designed for. These are to be used for all permanent bridges and culverts. IRC class B loading is to be adopted when the bridges, we have temporary bridges and timber structures. And the last one, the IRC special vehicle loading, this is to be adopted where the bridges are subjected to the passage of trailer vehicles carrying stator units, turbines, heavy equipment and machinery. So these are the 5 classes of loadings and their uses. So as we do for general structures, we go for a load combination. So here too we have got IRC 6 has given the load combinations to be adopted when we go for the analysis of the deck slabs. Now in this case of bridges, the load combination depends on the width of the carriageway. Now the width of the carriageway is defined as the distance between the inner faces of the curb or the footpath. Basically this is the distance or this is the length of the deck slab on which the movement of vehicle is permitted. So this is called as the carriageway or the carriageway width. So when your carriageway width is less than 5.3 meters, then that is designed as a single lane bridge. So class A load can be considered for the analysis. When the carriageway width is between 5.3 to 9.6 meters, then it becomes a 2-lane bridge. Then the deck slab can be analyzed for 1 lane of 70R or 2 lanes of class A loading. Similarly, for 3-lane bridges, that is for carriageway between 9.6 to 13.1 meters. So 1 lane of 70R for every 2 lanes and with 1 lane of class A on the remaining lane, or simply we can analyze it for 3 lanes of class A loading. Similarly, for carriageway width between 13.1 to 23.6 meters, where the number of lanes vary from 4, 5 and 6. For all these cases, the live load combinations can be 1 lane of 70R for every 2 lanes with 1 lane of class A for the remaining lanes, or 1 lane of class A for each lane. So depending upon the width of the carriageway, the appropriate live load combination needs to be adopted. So moving on to the analysis part. So as I've shown in the earlier slide that the analysis and the design of a deck slab involves various stages. The first stage is the structural configuration of the slab. That is, we need to understand what is the behavior of the slab, whether the slab is spanning in one direction or the slab spans in two directions. The next is the calculation of the loads. The primary loads on the deck slab are the dead loads and the live loads. So the dead loads are calculated from the weight of the slab itself, and the live loads are obtained from IRC 6. The next part is the analysis part. So in case of analysis, we come across two situations. Either the slab spans in one direction or the slabs may span in two directions. So what we have here is, when the slabs are spanning in one directions or cantilever slabs, the analysis can be performed using a method called as an effective width method. This method is also given in IRC 112, and also it is given in 456. And for the slab spanning in two directions or simply two-way slabs, the Pegas method is the most popular method used for the analysis. So now we will be discussing one by one what are these methods. First, we'll try to understand what is effective width method. So in case of one-way slab, the method that we adopt is the effective width method. Here, the live load transmitted by the wheels are regarded as concentrated loads which are dispersed over the tire contacts area with the deck slab. The bending moments are calculated by assuming the width of the slab as effective in resisting the bending moment due to concentrated loads. Now both these assumptions can be explained by this simple diagram here. So let's try to read this diagram here. So what I have here is, I have a simple slab, or rather I'll call it as a deck slab of dimension of length L0 and width B. This slab is resting on two opposite sides, and these sides we can visualize for the time being as the abutments. Now since the slab is supported only on two opposite sides, we are going to have a one-way action. So this slab is going to be analyzed and designed as a one-way slab. Let's consider a wheel load. So this is a wheel load carrying some load W, and this load is placed on the deck slab. So when the load is placed on the deck slab, what's going to happen is that the load is going to get dispersed through the thickness of the slab. So what we see here is that when the load is applied on the slab, the load gets dispersed along the length of the slab and across the length of the slab. That is, along the length and along the width of the slab. So what we need to do here is, we need to find out what is the effective length of the load along the span and what is the effective length of the load across the span. So this is called as the effective width method. So here I've used some more terminologies here. For example, this is B1. This B1 is the dispersion through the varying code, this which I'll be showing in the next slide. And B effective, what you see here, this is the effective, this is the length of the load that has dispersed along the width of the slab. This is the width of the load that has dispersed along the width of the slab, and this B effective is calculated by this expression as alpha times A into 1 minus A upon L0 plus B1. This is the expression which is given in IRC 112, and a similar expression is given in IS 456, where the slabs are designed for concentrated loads. So when we read this expression here, alpha is a constant which depends on the aspect ratio, that is B upon L0. A is the distance of the CG of the load from the nearest support. L0 is the effective length of the slab, and B1 is the width of the dispersion. So these things get clearer when we move on to the next slide, something like this. So there are two possibilities. So here, this is a one-way slab in which the slab is resting on two opposite sides. The other possibility could be a cantilever slab. Again, this is a one-way slab. So in case of one-way slab, the expression changes to 1.2 times A plus B1. So here the things become clear. So let's try to read this diagram here. I have a slab. I have a wheel that is placed on the deck slab. The darkened portion, let's say that is the wearing coat, and the light portion, what you see below, that is the structural slab. So when the load is placed on the deck slab, the load is going to disperse through the thickness of the slab. So the dispersion that happens through the wearing coat, or we can say the contact length of the wheel on the deck slab is given as B1, and the dispersion of the load through the thickness of the slab is called as B effective, and the distance of the CG of the load from the nearest support is given as A. So these are the parameters that are required to be inputted into this expression to get the effective length of the load that is acting on this slab. So this expression alpha, as I told you, this is a constant that is obtained from B by L ratio. So B is the width of the slab and L naught is the length of the slab. So for various values of B by L naught, alpha values have been given for simply supported slab and for continuous slabs. So these values are given in IRC 112. So let's have a better understanding of what we understand by dispersion, because when we try to visualize dispersion, and when I say the load is going to get dispersed along the length and along the width, it sometimes becomes very confusing. So let's try to simplify this definition here. Let's consider a wheel load here, and when let's say this wheel is now placed on a deck slab. So when the wheel is placed on the deck slab, B is the contact length of the wheel along the span, and W is the contact length of the wheel across the span. So these are the terminologies what we are going to use, and these are the terminologies which are going to remain consistent throughout the presentation. So let's try to understand what we mean by dispersion of load along the span. Let's consider a deck slab. Let's say this is the deck slab, this thing, and we see that the deck slab consists of a top wearing coat and the bottom structural slab. Now the load is placed on the deck slab and the axle load is, let's say, W. So when the load is placed on the deck slab, what's going to happen is that the load is going to disperse through the wearing coat and through the structural slab. So we can assume a dispersion of 45 degrees, and from that angle it is possible to calculate what is the length of the dispersion along the span. Please remember that the concept what is being described here is only applicable for one-way slabs. Since the load is being transferred only in one direction, that is along the length, so here the dispersion can be calculated by considering a dispersion of 45 degrees. So we can calculate the length of the dispersion from this simple expression. This is B, that is the contact length of the wheel along the length, plus 2 times the thickness of the bearing cord and the slab. So this is the effective length of the load that is acting along the length of the slab. Similarly, when I look in the perpendicular direction or across the span of the bridge, across the span, so this is how the diagram looks. So here we can consider, or here you can visualize that the wheel is moving perpendicular to your screen. So when I place this wheel on the deck slab, the width of the wheel is given as W. The dispersion that happens through the wearing coat up to the top surface of the slab is given as B1. So that B1 is calculated as W, that's the thickness of that's the width of the wheel plus 2 times the thickness of the wearing coat, and B effective, that is the dispersion of the load that takes place along the width of the slab, and that is given by this expression B effective. So when we have to calculate in case of one-way slab, what is the effective width of the dispersion of the load across the width of the slab, then that is calculated by this expression B effective, alpha times A into 1 minus A upon L naught plus B1. So these are the things that are required for calculation of shear force and bending moment by using the effective width method. So going ahead with this, so when we deal with the effective width method for one-way slab, then there can be 2 possibilities. So which will be again very clear in the coming slides. There are 2 possibilities. The first possibility is that on the deck slab, there could be two or more concentrated load that may act in a single line. Or in other words, the loads may be acting in a single line. Or the other possibility is that there may be two or more concentrated loads, but they may not be acting in a single line. So we need to calculate what is the effective width of the load on the deck slab for both these cases, and then try to calculate the bending moment and the shear force. So we'll take these cases one by one. First, I'll define these two cases, and then in the design example, I'll try to explain how the things have been taken care of. So the first condition is when two or more concentrated loads are acting in a line. So in such a situation, what is done is for two or more concentrated loads in the line, in the direction of the span, the bending moment must be calculated separately for each load based on its effective width of the slab. So this is the definition. So what exactly it means, we'll be seeing in the next slide. And in the second case, when two or more concentrated loads are not acting in a line, in that case, if the effective width of the slab for one load overlaps the effective width of the slab for an adjacent load, then the resultant effective width for the two loads equals the sum of the respective effective widths for each load minus the width of the overlap, provided that the slab so designed is tested for two loads acting separately. Though this looks a very lengthy definition, so it's a quite simple thing when we look at the diagram. So this I'll be showing it in the next slide. So to understand both these cases, that is when the loads are acting in a straight line and when the loads are not acting in a straight line, let's try to understand this by some worked out examples. So what I've taken is I've taken a very simple example to highlight what this effective width method means. So what I've done here is I've taken a simple slab culvert of span 6 meters. So this is a simple deck slab which is resting on two opposite sides, and the width of the carriageway is 7.5 meters. Let's say there is a footpath of 1 meter on either side. So the total width of the slab works out 9.5 meters. Let's consider that this culvert is subjected to IRC class AA tracked vehicle loading. So this is the loading what we are going to use for computing the bending moments and shear force. So IRC class AA tracked vehicle consists of a battle tank. Now this weighs 70 tons or 700 kilonewtons. The contact length of the wheel that it makes with the deck slab is 3.6 meters. The overall length of the vehicle is 7.2 meters. So if I take a cross section, this is how it looks. The width of the track or the width of the wheel is 850 mm each, and the distance between the wheels is 1.2 meters. And C is the clearance that is required for the movement of this vehicle. So IRC 6 has given clear guidelines that what should be the minimum distance that the vehicle should be placed from the edge of the curb or from edge of the footpath. For IRC class AA tracked vehicle, this works out to be 1.2 meters. So the objective in this problem is to calculate the design bending moment, and shear force for dead load and live load. So how do we do this? So let's take this simple example here and try to understand what this effective load method is. So first thing what we need to do is I'm interested to find out what is the bending moment that is produced due to the dead load. So since the dead load is a static load and it is spread uniformly over the entire length of the bridge, so I can calculate the weight of the slab. So what I've done here is I've multiplied the thickness of the slab by the density and I worked out the weight of the slab. Then weight of the bearing coat, again the thickness of the bearing coat and multiplied by the density, I've got the weight of the bearing coat and I've got the total dead load. So from the simple equations of equilibrium, I'll calculate the bending moment as WL squared by 8. Since this is a simply supported slab subjected to a uniformly distributed load, I can very straightforwardly get the bending moment due to live load. Now the things get interesting when we move on to the calculation of bending moment due to live load. So as we understand that the fundamental difference between the live load on building structures or general structures and bridge structure is, in case of regular structures, buildings, the live loads are static in nature. They do not vary with respect to time. But in case of bridge structures, the live loads are dynamic in nature. So when I look at this IRC class A loading, this is a vehicle, this is a battle tank, this is not a stationary vehicle. This is going to move along the span or along the length of the bridge. Now the question arises is where this load should be placed such that I get the maximum bending moment. So what we are going to do here is to arrive at the maximum live load bending moment, the live load should be placed in such a position that it produces a maximum bending moment. So for a simply supported slab, obviously the bending moment you're going to get maximum when the heaviest load is passing to the centroidal axis of your bridge. So in this case, the live load is placed centrally on the bridge. So now when the load is placed centrally on the bridge, what's going to happen is that the load is going to get dispersed through the thickness of the slab. Now this dispersion of the load is going to happen in both the directions. The load is going to get dispersed along the length and also across the length. So what we need to do is we need to calculate the dispersion of the load. So first what we do is we calculate the effective length of the load along the span, that is how much the load has dispersed along this length, and similarly what is the effective length of the load across the span, which is given as B effective. So we'll take the first case, the dispersion of the load along the length of the span. So what I've done here is I've taken this IRC class AA wheel tracked vehicle and placed it at the center. The contact length of the wheel on the deck slab is 3.6 meters. So when I place this load at the center, the load is going to get dispersed through the thickness of the slab, and this is going to be the length of the dispersion. So here the dispersion is happening through the varying chord and through the thickness of the slab. So for calculation, I've considered these values for the varying chord and the slab. So this length of dispersion can be calculated by adding up these things. So it is the width of the track plus 2 times the thickness of the varying chord plus the thickness of the slab. So this works out 4.760 meters. So what it means, a load that is placed on the top of the deck slab of 3.6 meters, that load is going to disperse through a length of 4.76 meters along the length of the slab. So I'll keep this value. I'll be using it at a later stage. So this is the dispersion of the load along the length of the slab. Next is the length of dispersion across the span. So just for clarity, I've taken these images, I've just put it here. So this is the cross section of the culvert. So what I'm going to do is I'm going to take this vehicle and I'm going to place it at the minimum clearance as mentioned in 112. So this clearance is 1.2 meters. So I'm going to place it here. So when I place it here, so these are the contact dimensions of the wheel on the deck slab. So the contact length or the width of the track here is 850 mm. So the in-to-in distance between the wheels are 1.2 meters and 850 mm respectively. So when the load is placed here, what's going to happen is that the loads are going to get dispersed through the thickness of the slab. So my objective here is to find out how much of the width of the slab is affected by this load. So first I'll do is I'll calculate the B1. This is the B1, this B1 is the dispersion of load through the varying chord. So what I'll do here is B1. So width of the load is 850 mm plus 2 times the thickness of the varying chord. So I end up with a value of 1.01 meters. So what is this 1.01 meters? This is the contact length of the wheel on the deck slab, or simply that is the dispersion of the load through the varying chord. So this is 1.01 meters for one wheel. So I'm going to use these values and try to calculate what is the dispersion that happens through the entire thickness of the slab. So for that, what I'm going to use is I'm going to use this expression, B effective. So alpha value I can calculate from the B by L ratio, that works out 2.48 meters. 3.2 meters. So what is this A? A is 3.2 meters. So A is the distance of the CG from the nearest support. So this works out 3.2. B1 that is the width of the dispersion through the vary code. So what I get? So I get the dispersion of the load along the width as 5.5 meters. So this is the length of the load that is getting dispersed through the slab. So this is for one wheel. So I can do it here. I can show it very nicely in the form of these graphics here. So I have this deck slab, I have these contact length of the wheel, and I can highlight the dispersion to these two colors here. So basically what I'm getting here is I'm getting the dispersion length as 5.5 meters. So here I can see here. So this is one wheel. So this load of 350 kilonewton is going to be dispersed through a length of 5.5 meters. Similarly, the other wheel is also going through dispersed through a length of 5.5 meters. But since the dispersion is going beyond the width of the slab, so the length will be considered up to the edge of the slab. So here we can see the dispersion or the effective width of the slab across the width is from this point to this point. And what we are doing here is, here we can see this is the region of overlap. So this is been subtracted, and this is going to be the total width of the slab which is affected by this load. Now this I can work out, and this works out to be 7.425 meters. So this 7.425 meter is the effective length of the load across the span, and similarly 4.760 is the effective length of the load along the span. So these are the two dimensions what are required for the calculations of your bending moment and shear force. So what I have here is I have the two dimensions along the length and along the width. So I know the total load of this vehicle is 700 kilonewtons. So from this, I can calculate the intensity of live load. So dividing the load by the area, I'll get something like this, 19.8 kilonewton per meter square. So this is the average intensity of live load. But when we are dealing with live load, there is one more factor that comes into the equation, and that is the impact load. So moving load produces impact, and that has to be accounted in the design. So what is done here is the live loads are multiplied by an impact factor to account for the dynamic effect which is produced by the moving loads. Though we are not going to have a rigorous analysis, IRC 6 has given some expressions for calculating the impact factor for different class of loadings. I'll quickly summarize what are these impact factors. So there are 5 different class of loadings. So typically those many conditions have been mentioned here. So the impact factor for class A or class B loadings. So for spans between 3 and 45 meters, the impact loading is given as 4.5 times 6 plus L, where L is the span of the bridge or the culvert. Impact factor for class AA loading and class 70R loading. So again, this has been given for 2 cases for spans up to 9 meters. For tracked vehicle, it is going to be 25% for spans up to 5 meters and linearly varying to 10% for spans up to 9 meters. And for wheeled vehicle, the impact factor is to be considered as flat 25% for spans up to 9 meters. For spans greater than 9 meters, for tracked vehicle, it is going to be 10 meters up to a span of 40 meters, and in accordance to this chart that is given in IRC 6. Similarly, for wheeled vehicle, it is going to be 25% for spans up to 12 meters, and according to the chart as given in IRC 6. So these are the things what are given in IRC 6 regarding the impact factors. So coming back to the problem at hand. So what we have an IRC class A loading which is acting on a culvert, and we have a span of 6.4 meters. And for IRC class A loading, the impact factor is given something like this. For span up to, it is 20, the impact factor is 25% for spans up to 5 meters and linearly reducing to 10% for spans up to 9 meters. So this is the variation of impact factors for IRC class A AA tracked vehicle loading. So for us, the span is around 6.4 meters. So from interpolation, I can calculate what is the impact factor. So this works out 19.7%. So what I'm going to do, impact is going to amplify the live loads, the effect of live loads. So what we are going to do here is we are going to multiply the live load with this impact factor. So this is 700 multiplied by the factor. So now the live load has increased from 700 to 838 kilonewton. So what I'm going to do here is I'm going to calculate the average intensity of live load with impact. So now that works out live load with impact divided by the effective area. Now this works out 23.7 kilonewton per meter square. So now we have the live load with impact for IRC class AA loading. Now I can simply calculate the bending moment using the equations of equilibrium. Since it's a simply supported slab and subjected to a live load of 23.7 kilonewton per meter square over a length of 4.76, I can calculate the bending moment. So this works out 113 kilonewton meter. So this is how we calculate the bending moment for live load. So this is the first part of the problem. The objective, if we can again go back, the objective of this problem is to calculate design bending moment for dead load and live load, and then design shear force for dead load and live load. So the first part was pertaining to the bending moment. The second part is for calculation of shear force. Now for the shear force, again as we have seen, the dead load is spread uniformly over the length of the bridge. So I know what is the total load and I know what is the effective span. Then I can simply calculate the shear force due to dead load. So this works out around 43.8 kilonewtons. So this is a straightforward expression. Now again the question comes is, what about the shear force due to live load? As we have seen earlier that the live load moves along the length of the bridge, so it can occupy, this live load can occupy any position. So again the question arises is where this load should be placed. Again, to arrive at the maximum live load shear force, the live load should be placed such that it produces a maximum shear force. So obviously if it was a concentrated load, then obviously the load would have been placed very close to the rear supports. So that would have produced the maximum shear force. But in case of these vehicular loadings, what happens is that the contact length of this vehicle is 3.6 meters. If I try to place it exactly on the support, what's going to happen is that part of the load is going to get dispersed away from the deck slab and part of the load is going to disperse into the slab. So that is not going to give me a condition of maximum shear force. So what is to be done here is the live load should be placed in such a way that the entire dispersion of the live load can be accommodated within the deck slab itself, and it is as close to the support as possible. So the condition is something like this. I have this live load of 3.6 meters here, and because of this live load, the load is going to get dispersed through the thickness of the slab. Now, our objective should be that this dispersion should be within the slab and it should be as close to the support as possible. So this is the condition what we have. So we have calculated this 4.76 in the next slide. So I'll show you how this is done. So this is how the shear force is calculated. So again, once we finalize the position of the load, then the next thing is we need to calculate what is the effective length of the load along the span and what is the effective length of the load across the span. So again, going back to the fundamentals, first we'll find out what is the dispersion of the load. First condition would be along the span. So this is your IRC class AA tracked vehicle. So again, the length of the vehicle, the contact length of the wheel is 3.6 meters. So when this load is placed, it is going to get dispersed, say through an angle of 45 degrees. So this total length can be calculated by simple expression. So this is the total contact length plus the load is getting dispersed through the thickness of the bearing cord and through the structural slab. So this is 2 times the thickness of the bearing cord plus the thickness of the slab. That works out, say, 4.76 meters. So what we know now, we know that the total dispersed length of the load along the span is 4.76 meters. So what we do, we fix this point, one end at the support, and we simply extend the other dimension to the other side. So this becomes the position for maximum shear force. So this loading configuration is going to give me the maximum live load shear force. So when I place this live load in this position, now we need to understand one more thing, is that the CG of the load has changed. Now the CG of the load is given by A. Now that works out 2.38 meters. So what is the difference? In case of bending moment, we had placed this load exactly at the center. At that time, the CG of the load was 3.2 meters, but now the load has moved towards the support, so the CG has shifted. So accordingly, the value of A changes into that expression to 2.38. So this is the dispersion of the load along the length of the slab. Similarly, the load is also going to get dispersed along the width of the slab. So that can be again calculated by using this expression. So this is what I tend to say. So I have this again, the slab, I have this wheel, this vehicle, and this is the dispersion of the load. So I am going to use this expression again. I'm going to input the value of alpha. A has changed now. The rest of the things remain the same. Now I can see that the effective width of the load is now 5.25 meters. So something like this. So if you can pay attention to this green hashed portion, so this is the dispersion of the load along the width of the slab. So this is for one wheel, this is for the second wheel. So again, we can see here, this is the common portion or the overlap portion. This has been deducted, and now we can calculate what is the total length of the dispersion. So here this works out 7.3 meters. So by adding these numbers, we can get the effective width of the slab along the width of the slab. So this is there. So I get the dispersion along the width. So I can again calculate the average intensity of live load by the similar expressions. I can add the impact factor. I can calculate the impact factor, and I can multiply this impact factor to this live load. And again, I can calculate what is the average intensity of the live load with impact. So now this expression gives me the average intensity of live load with impact. This is the load. So again, using the equations of equilibrium, I can apply this live load on the slab, and I can calculate what is the shear force. So from the equations of equilibrium, I can calculate what is the shear force due to live load. So for IRC class AA tracked vehicle, the shear force works out 67.5 kilonewton. So this is how we calculate the bending moment and the shear force for dead load and live load respectively. So in this example, what I had taken was, I had taken a tracked vehicle. I had taken a tracked vehicle where the calculations seem to be very simple, because there's going to be only one load that is going to act, and the calculations are fairly simple. I can extend the same example for a wheeled vehicle. So what I'm going to do here is, I'm going to take the same culvert here, but instead of a tracked vehicle, I'm going to analyze this culvert for a wheel loading configuration. So to solve this problem, what I've done, I have considered IRC class A wheel loading. IRC class A wheel loading. So this is the wheel loading I'm going to apply on the deck slab, and for this loading configuration, I'll try to calculate what is the design bending moment and what are the design shear force. So again, I'll go back to the fundamentals here. So again, I have a culvert of span 6.4 meters. So I'm interested to find out, the first thing is the bending moment due to dead load. So the dead load, the weight of the slab I can calculate by multiplying the thickness of the slab by the density. Weight of the bearing cord I can calculate by multiplying the thickness of the bearing cord by the density. I can add those together. That is going to give me the total dead load. Now this dead load is going to be spread uniformly over the length of the slab. So this gives me a very simple condition of a slab subjected to a uniformly distributed loading. So for this loading condition, I can straight away get the bending moment due to dead load. So that works out WL square by 8. So from this, I can calculate the bending moment. Now the things again become interesting when we go for the analysis for the bending moment due to live load. So a couple of things what we really need to understand here is that the problem what I have chosen here is slab culvert, and the width of the carriageway is 7.5 meters. And here I'm interested to analyze this problem or this deck slab for IRC class A loading. So if we recall back the live load combinations, so when your width of the carriageway is up to 7.5 meters, then you have to analyze your deck slab for 2 lanes of IRC class A loading, either 70R or 2 lanes of IRC class A loading. So for illustration, what I've done here is I'm going to analyze this deck slab for 2 lanes of IRC class A loading. So this is the IRC class A loading. So let's make it a little bit colorful. So this is how it looks. The front portion, the prime unit. Again, this is followed by a trailing unit, trailers. So basically this is how it looks. So this is the prime mover. So the front axle transmits a load of 2.7 tons. The second axle transmits a load of 2.7 tons, and the subsequent 2 transmits a load of 11.4 tons respectively. So something like this. So the front axle 2.7, 2.7, 11.4 and 11.4. And you can see here the subsequent trailer loads. The axle loads transmitted by these trailers are 6.8, 6.8, 6.8 and 6.8 tons respectively. So in this whole loading configuration, we can see that the highest axle loads are transmitted by these 2 axles. That is by the prime mover of. So this axle load are of 11.4 ton each. So what I've done here is, and also we need to understand here is that the total length of this vehicle is 8.3 meters. And also we need to understand here is the total length of our culvert is just 6 meters. So what it means that it is not possible for me to accommodate the entire length of this vehicle on this deck slab. So what part has to be accommodated? So we have to accommodate those axles which are transmitting the severest or the highest axle loads. So that is given by this part. So this is a diagram what I have highlighted here. So this portion of the vehicle is transmitting the highest axle loads. So again, if I look at this is an 8.3 meters vehicle, but our span is only 6.4 meters. Again, it is not possible for me to accommodate all these 4 axle loads. So at the most what I can do, I can consider these 2 severe loading conditions or the highest axle loads, and I can place it symmetrically about the centroidal axis. So this is a centroidal axis of the slab. So 11.4 kilotons on one side, 11.4 tons on one side. So I'll place it here. And again, if I see here, it's not possible. So the whatever length is remaining on the deck slab, again, this length is not in the position to accommodate any other axle loads. Neither this 2.7 meters or either those 6.8 tons, the trailing axle loads. So this slab is not in the position to accommodate all these axle loads. So what I'm going to do here is I'm going to analyze this deck slab only for these 2 axle loads. So 11.4 tons, 11.4 tons. But please remember that this is going to be a 2-lane bridge. It means that there are 2 axles of 11.4 tons on this side, plus there are other 2 axles on the just behind these 2 axles. So in all, I'll be having a combination. I'll be having a total of 4 concentrated loads of 11.4 tons. So again, when we look at these concentrated loads, again, to arrive at the maximum bending moment, the live load should be placed such that they produce the maximum moment. Obviously, what we are going to do, we are going to place these live loads symmetrically about the centroidal axis. So again, when these loads are placed, when these concentrated loads are placed on the deck slab, the loads are going to get dispersed through the length and across the length. So the next two things would be calculating the effective length of the load along the span and effective length of the load across the span. So this is what we have here. So I have this slab of 6.4 meters. So this is a centroidal axis, and I place this load symmetrically about the center. So when these loads are placed on the deck slab, the loads are going to get dispersed through the bearing core and through the structural slab. So along the length will be this, the total length of dispersion along length will be this length. So to calculate this 2.61 meters, I need to know what are the contact dimensions of the wheels. So IRC6 has given that B equals to 250 mm and W is equal to 500 mm. So B is this length, that is the contact length of the tire or the wheel along the span of the deck slab. So I can take this, and from this I can calculate the dispersion length of the along the span. So it will be 250 plus 2 times the thickness of the bearing cord plus the depth of the slab. So this works out 1410. So we can see here. So one wheel is going to disperse through a length of 1.41 meters. The other wheel is going to disperse through a length of 1.41 meters. So neglecting the overlap, so what we are going to do, we are going to calculate the total length of dispersion. So that works out 2.61 meters. So this is the length of the load that is effective along the, this is the dispersion length of the load along the span of the slab. Similarly, we need to know, or we need to calculate what is the dispersion length across the slab. So this is how it looks now. This is the cross section of the slab. This is the cross section of the slab. And when the wheel load is placed on the slab, so the contact length of the wheel is given as W. The dispersion through the bearing cord is given as B1, and the dispersion through the bearing cord and through the structural slab is given as B effective. So B1 can be calculated as 500 plus 2 times the thickness of the bearing cord. So this works out 660 millimeters. So B1 works out 660 millimeters. So next, the total effective width, or the B effective, again is calculated using this expression. So alpha times A 1 minus A upon L naught plus B1. So I substitute these values here. B1, after substituting all these values, so 2.6 meters, that is the CG of the load from the nearest support. B1 we have just calculated in the previous calculation. This works out 5.05 meters. So let's again try to read this diagram, how we have prepared this diagram. So again, this is your deck slab, this is your footpath, and this is your IRC class A loading, typical IRC A loading. So as per IRC 6, so when we are dealing with IRC A loading, wheel loading, the clearance that is required is 150 mm. It means that the vehicle has to be placed at a distance at least of 150 mm from the edge of the curb or edge of the footpath. So what I'll do is I'll place the first vehicle at 150 mm. The minimum overpassing distance between two vehicles as given in IRC 6 is 1.2 meters. I'll place that vehicle there, and then whatever remains, whatever is remaining, that can be calculated. So I start from one end. So I place these vehicles. So now I've seen that IRC class A loading, one wheel of 500 mm width is going to disperse the load through a length of 5.05 meters. So basically, when this load is applied, so let's take the central one. So the load is going to get dispersed. Let me do something like this. It is going to disperse through a length of 5.05 meters. So again, there is going to be an overlapping. So I've just not drawn these lines just to avoid the confusion of so many lines here. So something like this is going to happen, and this is something what we already have. So after subtracting all the overlaps, it is possible for me to calculate what is the total width of this dispersion. Total width of dispersion. So in this present case, what is happening is that the total width of the dispersion is exceeding the width of the slab. So in that case, the values are limited to the width of the slab to 9.5 meters. So the total width of the slab across the total width of the slab which is effective in resisting the applied load is 9.5 meters. So using these dimensions, I can again calculate the average intensity of live load. This works out 18.3 kilonewton per meter square. Then again, to this live load, I'm going to add the impact factor. So as we have shown in the earlier slide, impact factor for class A loading is calculated by this expression. So here, the impact factor works out to be 0.36. So I multiply this with, so this is the change what you see here. 114 into 4 because this is a 2-lane. So I'm going to multiply the total weight of the vehicle by this 1.36. This is going to give me the total live load with impact. So again, I'm going to calculate the average intensity of live load with impact. This works out around 25 kilonewton per meter square. So again from the equations of equilibrium, I can calculate what is the bending moment that is produced due to the live load. So I can write that expression and I can calculate that the live load due to the bending moment due to live load is 83 kilonewton meter. So this is significantly less than IRC class AA tracked vehicle. So this is how we calculate the bending moment due to live load. The second part of this is the calculation of shear force. Again, the shear forces are calculated for dead load and similarly for live load. So again, here as we see that for the shear force due to dead load, so we can directly get this by the expression WL by 2, where W is the total dead load. Since it is spread uniformly over the entire length of the deck slab, I can simply take it and multiply it by the length. I get the shear force due to dead load. Now things get interesting when we move on with the shear force due to live load. So again, let's try to understand what exactly we are doing here. So we are trying to find out the bending moment and shear force for a slab culvert for IRC class A loading. So this is how the vehicle looks. The total length of this vehicle is 8.3 meters and it has got 4 axle loads transmitting a load of 2.7, 2.7, 11.4 and 11.4 ton respectively. Now for this loading configuration, I have to calculate what would be the maximum shear force. So again, the most obvious question would come is where the live load should be placed such that it produces maximum shear force. So again, the answers remain the same. The whole of the dispersion should be accommodated within the slab and the dispersion should be as close to the support as possible. So when we have to calculate those things, then again, we need to calculate what are the lengths of dispersion along the span and across the span. So here this is the deck slab of 6.4 meters and this is the live load. This is the live load, total live load. And now the next question obviously would be where this live load should be placed. So this can occupy any position on this deck slab. So the live load would be placed in such a way that the dispersion produced by the applied loads are accommodated within the deck slab and the edge of the dispersion is as close to the support as possible. So this can be one possible configuration. So I just simplified the things here. So these two live loads can be placed here. This is the dispersion that is produced because of these two axle loads. So in case of shear force, it is also it's possible for me to accommodate even this axle load. So I place this live load also. This live load typically comes on the support, so I can neglect it. So here for the shear force calculation, I am having 3 axle load acting on the deck slab. So now I need to calculate what are these lengths of dispersion along the length. So the effective length of the load along the span. So what I'll do is I'll take the first one. This is the first axle load. So the load is getting transferred or dispersed through the bearing core and through the deck slab, through the structural slab. So 250 mm is the contact length of the wheel on the deck slab plus 2 times the thickness of the bearing cloth and the thickness of the slab. So this gives me 1.41 meters. Similarly, I can work out the thickness, the length of the dispersion of these two axle loads. So on the same lines, I can write this expression plus this is the spacing between these two. I can write it. So this gives me 2.61 meters. So what I'll do, I'll draw these dispersion lines and I will coincide the edge of the dispersion along the support and then adjust these loads. So this is the configuration of the loads, what I get for the shear force calculations. So this is the dispersion along the length. Similarly, we also need to calculate the dispersion along the width. So again, let's look at this diagram, the same diagram. So I have this deck slab, I have this wheel. The contact length of this wheel along on the deck slab is W. B1 is the dispersion through the bearing cord, and B effective is the dispersion of the load through the slab across the width. So for this, I'm going to use this expression given in 112, and I'm going to calculate what is the effective width. So here, the effective width of one wheel works out 4.45 meters. 4.45 meters. So what I'll do is I'll take this 4.45 meters and then just try to plot it here. So this is how it looks in the cross section. So this is our deck slab. These are the two vehicles which have been placed starting from this end, and these are the contact length of the wheels on the deck slab. So when these loads are placed on the deck slab, they are going to get dispersed through the thickness of these slabs. So these four color combinations, what you see, these are the dispersion of these individual wheel loads. So as seen here in the previous slide, the dispersion of one wheel load is 4.45 meters. So I've just shown one here for simplicity. So when the load is placed, the load is going to disperse through a length of 4.45 meters. Similarly, I can write out the dimensions for all these dispersions and I can calculate what is the total length of dispersion. So here the total length of dispersion I think works out 9.05 meters. So this is how I calculate the total width of dispersion across the span of the deck slab. So once I have found out the length and the width of the dispersion, then I can calculate the average intensities. So again, I can simply take these live loads and again divide it by the length and the width. That gives me the average intensity of live load. I can calculate the impact factors, I can multiply it, and then I can calculate the average intensity of live load with impact. That gives me 29.3 kilonewton per meter squared. So now I know what is the intensity of live load for calculation of shear force. Since it's a simply supported slab, I can simply apply this load, and from the equations of equilibrium, I can calculate what is the shear force. So here, the shear force works out 60.3 kilonewtons. So this is how we calculate the bending moment and shear force for wheeled vehicle. So coming back, so here we have seen that when we look at the structural configuration of the slabs may be one-way slabs or they may be two-way slabs. So if it's a one-way slab, then what we can do is we can use the simple effective width method for calculating the bending moment and the shear force. But in some cases, say for example in typical T-beam deck slab bridges, where the slab is resting on all the four sides, you may have a slab which may span in both the directions. At that time, we have a two-way action of the slabs. In such a case, we cannot again go for the conventional analysis. So here, the method that is more popularly used is the Pigard's method. So this Pigard's method is used for calculating the bending moments in a two-way slab. So let's see what this Pigard's method is. So this method is applicable for calculation of bending moment for slab spanning in two directions. But before we understand, before we go into the detail, before we go into the example of solving this problem using this method, let's understand what are the limitations of this method. So this method is only applicable, this is very important now, is only applicable if the slab is rectangular in shape and the slides are simply supported or freely supported. Second, and the most important thing is, this method is only applicable if the loads are placed centrally on the slab. It means that if the loads are not acting centrally, then this method cannot be used directly. Then we have to go for some modifications, which I'll be demonstrating in the next few slides. So please understand this. The limitations of this method is the slab has to be rectangular and the load has to be placed symmetrically about the axis of the slab. But when we speak of, say, for example, of T-beam deck slab bridge, there we don't have a condition of freely supported slabs. There the slabs are continuous and they are held down. In such a situation, it has been found out that in case of two-way slabs, which are continuous in nature, it is found out that the span movements can be reduced by 20% as though obtained for freely supported slabs, and the results are satisfactory. So we can go about this and design or analyze a two-way slab. So let's see what this Pigard's method is and how it is to be adopted. So to understand this method, we'll just consider a slab. So let's say I have a slab of dimension B and L. So where B and L or L and B are the dimensions of the slab in the long and short directions. Let's consider that for convenience or for simplicity, let's assume that these slabs are supported on girders and cross girders. They are supported on all the four sides. These two axes are the centroidal axis of the slab. And let's consider that a wheel load is placed centrally on this slab. The wheel is placed centrally on this slab. Now, when the wheel is placed centrally on this slab, let B and W, I've just changed the notations here. Earlier, B I had used the uppercase. Now I'm using the smaller case just to distinguish with this B. Here, B and W are the dimensions of the tire or the contact length of the wheel on the deck slab, B and W. So something like this. So I've just taken a cross section along the center of this wheel. So what I get here is, this is the cross section of a slab. This is the wearing code. This is the structural slab. The wheel is placed centrally and it carries some axle load P. So the contact width of the wheel on the deck slab is given as W. So these are the notations what I have used. Other than that, we have two more notations, U and V. So we have seen earlier that when a load is placed on the deck slab, the load gets dispersed through the thickness of the slab. So the dispersion length are given as U and V. So when the load disperses along the length, it is going to be V. When the load disperses along the width, it is going to be U. So U and V are the dispersion of load through the slab in the long and short directions. So based on these conditions, Pigard has given some charts wherein we can calculate the bending moment coefficients. And those bending moment coefficients depend on a couple of factors. The first is the aspect ratio, K, that is the ratio between B and L, and these values, U, V, and B and W, U and V ratios. So I'll be showing that in the next slide. So what Pigard has done is that he has solved these plate problems and he has given some charts wherein it is possible to calculate or obtain the bending moment coefficients for a slab subjected to a concentrated load acting at the center of the slab. So these charts can be read for different values of K, where K is the aspect ratio, and for different values of U by P and V by L ratios, where U by B is, this is the U, this is B, this is V, and this is L. And K is the ratio between B and L. For different values, he has given these charts. So from these charts, we can get the values of the bending moment coefficients M1 and M2. These are the long ball and the bending moment coefficients along the short and long spans M1 and M2. So the bending moment again can be calculated by this expression. This expression is very similar to those given in IS 456 for calculation of bending moment for two-way slabs, or the Rankine-Grashof equation, where M1 and M2 are the bending moment coefficients. Mu is the Poisson's ratio, and Picardy has used the value of mu equals to 0.15. And P is the load that is acting on the slab. So using these values, it is possible to calculate the bending moment along the span and across the span of your deck slab. So this method can be described by solving a simple example. I've just taken a simple example here just to highlight this Pigar's method. So what I've done here is I've taken a simple slab panel, a simple panel of dimensions 4 meters by 2.5 meters. And what I've done here is I've considered the thickness of the bearing coat as 80 mm and the thickness of the structural slab as 200 mm. And I want to analyze this slab for IRC class AA tracked vehicle. So I can solve this problem, and the same analogy can be extended for any class of loading. So this is what I have intended to do. So I want to find out what is the bending moment that is produced by this IRC class A tracked vehicle. So let's try to understand this. So again, I have this slab, I have this loading. Obviously, the first question that comes to the mind is where I should place the load. Now, the question sometimes is simple to answer and sometimes it becomes very tricky to answer. So for this, we need to look at a couple of things. First is we need to understand what is the length and the width of the slab. So the width of the slab is 2.5 meters. This is one thing. Now, next thing we need to understand is what is the width of the live load vehicle. So the width of the live load vehicle is 850 plus 1.2, 1.2, I think this works out 2.9 meters plus this clearance. Or let's say, to keep it simple, the total width of this IRC class AA vehicle is 2.9 meters, but my slab is only 2.5 meters wide. So first and foremost thing is that it is not possible for me to accommodate this entire vehicle on this slab. It's not possible. So what can be done is I place one wheel of this vehicle symmetrically about the centroidal axis. One wheel. So this I can accommodate very comfortably. So what I've done, I've taken one wheel and I've placed it symmetrically about the centroidal axis and I've placed it here. So what I get here, so here we can see the contact length of the wheel along the length is 3.6 meters. So I have 3.6 meters. So I have taken 3.6 meters. So here you can see the contact width of the wheel on the deck slab is 850 mm. So 850 mm. So now what I've done is I have placed this wheel load symmetrically about the center. So by doing this, I am doing two things. The first thing is that I am accommodating IRC class AA tracked wheel vehicle wheel loading on this slab. And second most important thing is I am satisfying the requirement of the Pigar's method. The Pigar's method requires that the load has to be placed centrally about it has to be placed symmetrically about the centroidal axis, or it has to be placed centrally on the slab. So by placing this wheel in this configuration, I am satisfying the requirement of the Pigar's method. So when I place this load on the slab, obviously, so the total weight of this vehicle is 700. So one wheel is going to weigh 350. So what's going to happen is when the load is placed on the deck slab, the load is going to get dispersed through the thickness of the slab. So I have this 850 mm, that's the contact length of the wheel on the deck slab, and this is going to be the dispersion. This is going to be the dispersion. So my objective here would be to calculate what is the dispersion of this wheel load along the length and along the width of the slab. So once I place this, so I'll just simply work out this. So I'm just taking forward the same diagrams here. I have these wheel load, this is the dispersion. So I'll try to solve this. So P is 350 kilonewtons. K is the aspect ratio B by L, that is 0.62. U is the dispersion of the load in this direction along the width. So that I can calculate by 850 plus 2 times the thickness of bearing cord plus the thickness of the slab. This gives me 1.41 meters in this direction. That is U is equal to 1.41 meters. V, that is the dispersion of the load along the length. So when this load is placed, so to what length this is going to get dispersed. So here, this is 3.6 meters. This is going to be 3.6 meters plus 2 times the thickness of the bearing cord plus the thickness of the slab. So this works out 4.16 meters. But the slab panel is only 4.4 meters. So V is limited to only 4000 millimeters. So I have P, I have K, I have U, I have V. So to refer to the Picard's curve, I need 2 more values. I need U by V and V by L ratios. So U is 1410, B is 2500. I can get U by V ratio. V is 4.16 and 4 meters respectively. I get 1. So I can use these. So what I can do is, so for K equals to 0.62. So there are different charts. There are different charts for different K values. So we have to interpolate even between the charts. So for simplicity, what I've done is I've just taken a chart of 0.6. So I've chosen the point of 0.6. I know what is U by V ratio is 0.56. I know V by L is something like this. So I can pull out the value of M1 from this chart. I can get the value of M1 from this chart. Similarly, I have these ratios. I can get the value of M2 from this charts. Okay. I can get the value of M1 and M2 from these charts. So I got M1, I got M2. I'll plug these values in this expression. So it is possible for me to calculate the bending moment in the shorter direction and in the longer direction. So this is how we calculate the bending moment in case of a two-way slab system. So this was a very simple case where only one load was placed. One load is placed symmetrically, so the calculations are fairly very simple. But not all the times we get such loading configurations. So I'll just try to explain those two conditions and come to the end of my presentation here. So there are possibilities. If you can recall back earlier, I mentioned that there are two possibilities. Either the live loads may be acting in a single line or they may not be acting in a single line. So this is the case this is the case what I'm trying to explain here. So let's see here, I have a slab panel B and L. So I've taken L, and let's say there are two wheel loads that are not acting at the center. So the wheel loads, the contact length of the wheel dimensions are B and W respectively, and U and V are the length of the dispersions. And let's say that these wheel loads are separated by a distance L1. And the end distance between the dispersion is, let's say, L. So for these conditions, it's not possible for me to apply the Picard's curves directly, because the Picard curves, what it requires is that the load has to be placed exactly at the center. But here it's not the case. So here we need to do some modification. So what we do here is, so I know I can calculate the dispersion for individual loads. I can calculate U, I can calculate V. So what I'll do is, I'll create a dummy load. I'll call it as D1, dummy load 1. So this dummy load 1 will have a width of V. since width of V is same for both the wheel loads, so I'll consider the width of the dummy load as V, and the length will cover the entire length between the end to end of the dispersion. So this is going to be my dummy load. So when I place this dummy load on the slab, what I'm doing, I'm fulfilling the requirement of the Pigard's method. The load is placed symmetrically about the centroidal axis. So for this, I can calculate the bending moment. So I can refer the Pigard's curves. So I can get the value of M1 and M2. I can calculate the bending moment. So for this condition, I can calculate the bending moment. I'll call it as the bending moment due to dummy load 1. Now, but this is not the case. This is not what I want. I want bending moment for these two conditions. So what I'll do here is, I'll create another dummy load 2. So as we know, I know what is the width of the dispersion, that is V, and I know what is the in-to-in distance between the dispersion. I'll call it as L1. So I'll apply one more dummy load of width V and length L1. So by doing this, what I'm doing is, again, I'm placing a load which is acting centrally on the slab. I can calculate the bending moment for this loading configuration. I'll call it as bending moment due to dummy load 2. So I have dummy load 1, I have dummy load 2. So what I can do is, I can simply subtract these things. So the design bending moment for these loading conditions can be calculated by subtracting the dummy load 1 from dummy load 2. So if I subtract this from this, whatever remains is the bending moment that is produced due to wheel load 1 and wheel load 2. So this is how we go about trying to solve the problem for such type of loading. There is one more case that is possible, something like this. It's just the extension of the previous one, but fine. So let's try to understand this. So I have a slab B and L, and I have a wheel load following another wheel load. So I have a wheel load 1, which is placed at the center of the slab, and there is a trailing wheel load, wheel W2, placed at this end. And I'm interested to find out what is the bending moment that is produced for this loading configuration. Again, Pigard doesn't give me any option to calculate the bending moment for such a loading configuration. Again, I have to go about this method. So what I'll do here is, I'll first consider the centrally placed load. This one, wheel load 1. So for this wheel load 1, I can calculate the bending moment using the Pigard's method. So this is that, I'll call it as the bending moment due to wheel load 1. So I'll get the bending moment for this. Next, what I'll do, I'll consider the wheel load 2. I'll place the wheel load 2 here, and I'll place one more wheel on the other side, symmetrically opposite to this. So I can calculate what is the dispersion along the width. I can calculate that. Then what I'll do, I will create a dummy load 1, which extends from one end to the other end, something like this. So the length will be equal to the end to end of dispersion. The width will be equal to the width of the dispersion of wheel load 1 and wheel load 2. So again, by doing this, what has happened here is, I am creating the load which is acting symmetrically about the centroidal axis. So it is possible for me to apply the Pigard's method. From this, I can calculate the bending moment due to dummy load 1. So I have done this, but I'm not interested in this. I need to do some more modification. So what I'll do here is, from this whole load, I'll try to deduct this load, the load between the dispersion, between the inner faces of the dispersion. So when I deduct this load, I'll call this as dummy load 2. So when I deduct this dummy load 2 from this dummy load 1, what I get is, I get the bending moment because of this and this. So I have all these configurations. Then I can simply do an algebraic sum here. So design bending moment, I can write an expression. Bending moment due to this load, yes, I want this because this is load is present here, plus half of bending moment 1, bending moment due to dummy load 1 minus bending moment due to dummy load 2. So by doing this, what is happening here is, I am subtracting this portion and I'm ending up with this configuration. So this is how we go about with using the Pigard's method for solving for deck slabs which are subjected to loads which are not acting at the center. So this method describes how to calculate the bending moment coefficients, bending moments for a two-way slabs. The last step after this remains is the design. So as it was discussed in the last week, Umesh had already discussed that if you want to design flexure element, then the designer has a flexibility to choose any of the three methods which are prescribed in IRC 112. So using the design bending moment and shear force calculated in the analysis, we can proceed with the design of the deck slabs. So with this, I have come to the end of my presentation.
Thank you.
Thank you.